All right, now that we've introduced two-dimensional curl and divergence for a vector field, let's look at problem 5. It says compute the two-dimensional curl and divergence for each vector field. What do you notice? And part A is this radial field that we introduced back in section 15.1. So F here is xi plus yj, and our I component, P, is x, and our j component, Q, is equal to y. So to compute the curl of this vector field, we're going to compute this quantity partial q partial x minus partial p partial y. And the x derivative of q is 0, and the y derivative of p is also 0, so this is just constant 0. And since this is equal to 0 for all points in the xy plane, we say that this vector field is irrotational on all of R2. All right, so then for the divergence, we want partial p partial x plus partial q partial y. And so the x derivative of p is 1, and the y derivative of q is also 1. So this is just constant 2. All right, so then as far as interpreting these values, well, let's first think about what's happening at the origin. Okay, so if I draw a little circle here centered at the origin, well, our field is acting radially, right? And we said that the curl is measuring the rotation of the field near, in this case, the origin. Well, if we're acting radially outward, there is no rotational tendency created by this vector field, so it makes sense that our curl would be 0 there. Okay, now for the divergence, that's measuring the flux density of the field, right? And so since I see this net outward flux from the origin, it makes sense that the divergence is positive there. Okay, now if I move to another point in the xy plane, like let's say right here, well now there is going to be a certain rotational effect that's going to be created by, say, vectors over here wanting to push, say, this little, think about a little paddle wheel placed at this point, right? It's going to want to push it this way, but see, since our vector field's acting radially outward, you're going to get an equal but opposite push in this direction, and they're going to wind up canceling out, and you still will have no rotational tendency created there by the vector field. So again, it makes sense that the curl is 0. Now for the divergence, now you are going to have some inward flux here. Okay, so that would contribute something negative when it comes to divergence. But since the magnitude of these vectors, right, are growing the further you move away from the origin, the outward flux is going to outweigh the inward flux, and so you still are going to come out with this positive 2 for your divergence. All right, so now let's move on to the rotation field. Okay, we also looked at this field in section 15.2. So our I component P is now minus y, and our J component Q is x. So to compute the curl, we want partial q partial x minus partial p partial y. And so the x derivative of q is 1, and then minus the y derivative of p, and that would be negative 1. So this comes out to be 2. All right, now the divergence, which is partial p partial x plus partial q partial y. Well, here the x derivative of p is 0, and the y derivative of q is also 0. So now we have a 0 divergence. Okay, so you can see there's just this flip-flop from what we saw in part A. Also want to point out here that since the divergence is identically 0 at all points in the xy plane, we call this vector field source free on all of R2. All right, so now let's interpret the answer. So if I say draw a little circle centered at the origin here, well, again, the curl is measuring the rotation of the field nearby your point. Okay, so if I'm close to the origin, I can see that this rotation field is going to create this counterclockwise rotation, so it makes sense that I would see a positive curl at the origin. For the divergence, well, this is measuring the flux density right nearby this point, and since we're working with this rotation field, okay, all of the field vectors are going to be tangent to this little circle, and so they're not going to actually create any flux, either inward or outward. Okay, so it makes sense then that the net flux would be 0, and so the divergence is 0. Now, if I place, say, a little circle over here, imagine putting a little paddle wheel in this location, well, again, we're going to get this rotational tendency that's created by the field. Okay, now for the vectors hitting the paddle, say down here, okay, they're going to want to push this thing clockwise. But see, out here, these vectors, they have greater magnitude. They're going to rotate that wheel counterclockwise. And since they have greater magnitude, they're going to outweigh these vectors. And so you still will see that counterclockwise rotation that's created by the vector field. So it makes sense that the curl is still positive out there. And then for the divergence, well, now, right, you are going to have some some inward and outward flux, okay, but now really by the symmetry created by the field, okay, you're going to have inward and then outward flux, and they're going to cancel out, okay, say down here as well as up here. So you can imagine fluid going in and then going out, okay, but the two contributions are going to cancel and you're still going to wind up with a 0 divergence. All right, great. And so now lastly, C, F is just yi. So pretty simple vector field here. We just have our P is y here in this case. So for the curl, which is partial q partial x minus partial p partial y, well, the derivative of q is just 0 because q is 0, and the y derivative of p is 1, so this would be negative 1. All right, and then for the divergence, this is partial p partial x plus partial q partial y, and the x derivative of p is 0, and of course the y derivative of q is also 0, so this is again a source-free vector field. All right, so now let's go ahead and look at a picture of this vector field. So the divergence is 0 and the curl is constant negative 1. So here's a picture of this field, and you might say, well, I don't really see any rotation created by this field, right? Because all these vectors here are parallel. Well, be a little bit careful here. So let's first start with, say, putting our paddle wheel right here at the origin. Okay, so now if I draw a little circle centered at the origin, okay, so these vectors down here are going to want to push the paddle wheel and create a clockwise rotation. Now these vectors up here are just going to reinforce that. So you will get some rotation created by the vector field, and it is clockwise, so it makes sense that the curl is negative. Okay, now what about the divergence? Well, like down here you're going to have some inward flux, and then you're going to have some outward flux. Okay, but really by the symmetry, because notice it's along each one of these horizontal lines, the magnitude of all these vectors are the same. So you're going to get just cancellation from the two contributions, both below and above the x-axis there. All right, so what if we were, say, located up here? We drew a circle here and think about a little paddle wheel. Well, this is a little bit more subtle. Now you're going to have these, these vectors down here that are going to want to be pushing the wheel to create a counterclockwise rotation. But see, as you move vertically upward, the lengths of these vectors grow. And so these vectors up here, which are creating a clockwise tendency, okay, their greater magnitude is going to outweigh the counterclockwise tendency created down here. So you still will see this clockwise rotation. All right, and then really the same argument for the divergence. You're going to get inward and outward flux, but they're just those contributions will cancel out. All right, well, that's going to do it for this problem. In the next video, we'll go ahead and see now the connection to Green's theorem and this stuff with curl and divergence. All right, I'll see you there.